My name is Aida Galfione, and as I was introduced, and I'm a PhD student based in Politecnico di Torino. My supervisor is Professor Alessandro Battaglia, who is advising work. And as well as him, I want to thank also Professor Pablo Scoglias, who I'm working with, and Elsa Cattani from ISAC CNR, and which we are working for this comparison that I will present today. So today I will talk about observing and characterizing convection using EarthCARE CPR data and geostationary imagery. I will go through a brief introduction on convection and the objective of the work. Then I will go through some examples of case studies that we are using to analyze the synergy between EarthCARE CPR and geostationary instruments. And then I will end with global statistics on, let's say, work in progress global statistics on convection. So when we talk about convection, it is we know it has a crucial role in the Earth budget for energy, moisture, and in the global circulation. And it is, but it is still very poorly understood from the from what happens in the inner cores of convection. So the inner dynamics of the convective cores is not well modeled yet. And this is because also there is a lack of observations of the global convection, because ground-based systems are very localized, so they can provide good observation, but very localized, so they can penetrate the cores, but they are only available in very small areas of the world. And instead, for what concerns spaceborne instruments, they can't in general either penetrate the clouds like the passive systems, or they can, but they can't measure, for example, vertical air motion. With EarthCARE, that was launched in May 2024, so almost 2 years from now, we had for the first time the Doppler capability of a spaceborne radar. So there are availability of data that measure the vertical velocity within clouds, because it can penetrate. Of course, there are problems, there are challenges to be addressed inside convective cores. For example, the very narrow Nyquist range, so the very narrow range of velocity that can be measured due to the PRF that is used by this instrument. So to better introduce what I'm talking about, for example, this is a scene. This is a convective scene. This is a big convective storm occurred on September 2024 in the Mediterranean Sea, close to the Italian coast. And this is a big system already quite deep developed. This is level 1 data from the ESA side, let's say. And this has already developed an anvil on the top of it. And but there is still a very active core, convective core here, that is also overshooting the tropopause here, because the updraft here is very strong. Also, we can't see the surface here because there is a very strong multiple scattering effect. Still focusing on this case study, we see that this is the reflectivity when it is filtered, when secondary echoes and surface clutter and the noise around is filtered out. And we say that this is the stronger updraft within convective cloud. This is the overshooting top, and this is instead what we can see when we look at the same storm from the geostationary image. So the objective of this work is mainly to compare the single storm from how it is seen by the EarthCARE CPR and by the geostationary, to reconstruct its history and to put it into the context of its life cycle. And then once all the convective stores are detected and characterized, we want to have a general statistics on the global convection. So when we look at the, as I was saying, from the Metasat second generation image, so the passive sensor infrared image, we see that the EarthCARE overpass, this red line, it's exactly this very cold area, so around 220 Kelvin, and it passed through it like in the middle. This star is the one corresponding to the location of the overshooting top. Looking at the Doppler, 1 kilometer resolution Doppler from the level 2 data of EarthCARE, we see that there is high variability of the velocity in correspondence of the convective core. The high variability is expected, and this is one of the signs of convection, of the features of convection. To better explain what I mean by variability, here I show a profile. This is the one corresponding to this dashed line. This is the reflectivity, and we see that there is strong attenuation below this maxima, this purple maxima. And then this instead is the Doppler profile. Here there are big jumps between subsequent pixels in vertical. And these are what we call aliasing, because as I was mentioning before, one of the challenge of the Doppler, of the EarthCARE Doppler, is that we have a very narrow Nyquist range, but more or less between minus 5.5 to plus 5.5 meter per second. And so this is the only range that EarthCARE Doppler CPR can measure. So if the velocity is outside this range, it falls within this interval. And so we don't really know what is the true, and it is very difficult to do the unfolding, also because of the lack of reliable boundary conditions, either at the top or at the bottom. In general, below the freezing level, as you can see here, we can say that everything is positive, so everything is going downward because there are hydrometers falling. But concerning the part above the freezing level, it is very difficult to understand what is really an abstract or not. So in general, we expect, as I was saying, we expect very strong variability in convective regions, and instead in stratiform region, we expect the Doppler to be within -2 and +3 meters per second. To try to better classify the updrafts, at least at the top, we were trying to use the geostationary images that have a much wider spatial coverage, and but unfortunately not so frequent in time coverage, meaning that we have images every 5 or 10 minutes, depending on the instrument, and the resolution is much coarse because it is 3 kilometers at the equator. So as you can see here, also the geostationary sees the overshooting top with colder spots, but it is a short-lived phenomenon, and so only in after 10 minutes it is already 10 or 20 minutes it is already lost by the geostationary passive imager. What we try to do is, with the SAF software, we try to detect and track this storm, and also to detect the overshooting top. It does it quite in a good way, and it classifies it as a growing system. So it is still growing even though the system is there since few hours. So it is already well developed. Okay, this is another example of another convective storm. These are mainly two bigger cells, and this is the first cell that would be detected, and this is the second, let's say, a group of cells, because one can be here and the other one can be here. What I want to show here is that in general, what we want to start detecting are the convective cores, but based on convective profiles. So in the literature, what was done also for CloudSat was based on reflectivity features. They could identify convective profiles by using these constraints. So continuous echo profile in reflectivity from 2 to 10 kilometers above the surface, and also profiles, and these profiles have to have 10 dBz level above the 10 kilometers. And in this case, for example, we would have detect as convective this cell, basically all this set of profiles. But the high variability in the Doppler is also here in this other cell, and this wouldn't have the detected by this criterion because it is too low. The cloud top is too low, and so we are proposing another criterion that is still under evaluation and that can be tuned according to the different convective strength. That is to use this proxy of very high variability in the Doppler to detect the convection. So in particular, we are counting the number of foldings, so the number of aliasing of the Doppler in only above the freezing level. And the same, we are counting the number of pixels outside the stratiform region, so outside -2 + 3 meters per second, to identify the convective profiles. And you can see that these basically match the design numbers. These two cells are also observed, of course, by the geostationary imager, and this is the visible field of the geostationary with the EarthCARE overpass, and this instead is the MSI image at the same time of the EarthCARE overpass, of course, that is giving a wider context to the two clouds. This is the MSG, so Meteosat image. This is the closest in time to the EarthCARE overpass. So we see that we are hitting a cold spot, but the resolution is sensibly different with respect to the MSI, which has 500 meters resolution. And this is a big problem of the Meteosat images, because we are losing a lot of details due to the low resolution. And this instead is the second cell. Again, we are around 220 degrees in the core of the cell, but we are just hitting basically the side of the cell. So here, going to a global perspective, what we are trying to do is to classify the convective profiles and to try to give a global analysis of the convective, where it occurs and how it is characterized. And first, we tried to use the EarthCARE data, 1 year of data, 2025, and we try to detect all the profiles who had these reflectivity features of continuous echo in reflectivity 2 to 10 kilometers above the surface and the 10 dBz level above 10 kilometers. And these are the percentage of convective profiles over the cloudy profiles in the EarthCARE data. So 1 year of data, and we clearly spot the main convective areas over the globe, so the Pacific, Congo, and here Brazil and Argentina. This is a 5 by 5 grid pixel. This is instead the same analysis, but done with the new dynamic criteria that uses this proxy of convection, that is the number of foldings higher than 2, only in the frozen part of the cloud, and the Doppler velocity pixel, the number of Doppler velocity pixels exceeding the stratiform region. We see that again, the more counts are in the area where we expect to have higher counts, and we see in the tropical band the main convection, but it is a bit more spread, and less, in general, less profiles are classified as convective. Okay, then we try to focus on the different areas where we expect more convection to see if we could see with this EarthCARE Doppler velocities analysis to see the different vertical structure of convection that we expect as from the literature, for example, in Congo and in Pacific, and also in the South America. So here with the red squares, I identify for spots where we expect to have strong convection, and these are the CFAD, so the reflectivity versus height scheme of the profiles that are classified as convective within these areas. And we can see that the CFADs are different. And for example, looking at the Pacific region with respect to the Congo region, we see that the Pacific region has more like spread in height, high reflectivity, meaning that probably has more cores that develop more close to the surface within a big storm, with respect instead of the Congo region that has probably a more defined single tower. To go further in this analysis, what we did was to compare the different within this different region, the number of foldings and the number of Doppler pixel that exceed the stratiform region to evaluate our criterion. And what we found is that, for example, Argentina, this purple line has more variability per kilometer, so more folding per kilometer within these profiles with respect to the other region, especially with respect to the Congo. And this may be indicating that we have stronger and more vigorous convection here, which is what is expected. Same here, we did the 1 minus CDF. So to highlight the deeper convective profile, and this is again the number of foldings per kilometer within these profiles, and again Argentina has more vigorous convective cores, even if less deep probably with respect to Congo. Of course, this analysis based on the single profiles may not be very robust, because very likely more profiles belong to the same convective core, and also there are not enough different convective cores and profiles to have a robust statistics. So what we are now trying to do is to do the same global statistics, but with a different approach. So trying to cluster the convective cores. So to, instead of going profile by profile, to analyze the single cores all clustered together, and then to give an analysis on and a characterization with the proxies of convection based on the Doppler, so number of foldings and the variability of the Doppler velocity field for the cores, and then have a global statistic. But this is still work in progress. So I want to conclude just saying that by summarizing what I was trying to explain, that is the Doppler velocity in convection observed by EarthCARE CPR is very challenging to be interpreted, and due to scanning reason. And this can be, the vertical velocity in convection can be better analyzed also using the synergy with geostationary passive instruments, but they have other problems in terms of spatial and temporal resolution. Using the Doppler velocity variability, we can have proxies for identifying and track deep convection. But also these can be has to be applied not only to the single profiles as was done before, but may be useful to be used as a proxy, as a metric for classifying the convective clusters. And I thank you for your attention.